Welcome to this video on fiber optic communication. In this video, we will be looking into one of the optical sources, laser, light amplification by stimulated emission of radiation. We will be discussing about the principle of operation of laser, the various configurations of laser, the derivation for lasing condition, resonant frequencies and quantum efficiency, and the modulation and temperature dependence of laser. In the previous video on LED, we had compared a laser with an LED. A laser provides high intensity, coherent, narrow beamwidth light which occupies low spectral width, and it is widely used for optical communication applications. The disadvantage of laser is its high cost, high temperature dependence and short lifetime. Now we shall discuss on the principle of operation of a laser. The laser action is mainly due to absorption, spontaneous emission and stimulated emission. An electron in the lower energy state absorbs energy from an incident photon and gets excited to a higher energy state. After some time, the electron drops to the lower energy state, emitting a photon, and that is called spontaneous emission. If a photon impinges on an electron in a higher energy state and stimulates it to drop to a lower energy state, thereby emitting a photon which is in phase with the incident photon, that is stimulated emission. Under thermal equilibrium conditions, the number of electrons in the excited state is very less compared to that in the lower energy state. Therefore, when photons are incident, there is more of absorption and electrons get excited from the lower state to the higher state. In order that stimulated emission exceeds absorption, the number of electrons or electron density in the higher energy state should be more, and this is called population inversion. In order to have population inversion, that is higher electron density in the higher energy state, pumping can be done. The energy difference between the band gap and the frequency of the photon emitted is given by Planck's equation, which is given as h nu is equal to E2 minus E1, where E2 minus E1 is the energy difference between the two states and h is Planck's constant and nu is the frequency of emission of the photon. Now we will look into the principle in detail. So absorption, it is when an electron or atom gets excited from a lower level energy state to a higher energy state, and spontaneous emission, this is a photon that is emitted when an electron drops to a lower energy state on its own. These emissions are isotropic and random phase. Stimulated emission is when another photon impinges on an electron and stimulates it to drop to a lower energy state. The emitted photon is in phase with the incident photon. Population inversion, that is number of electrons in the higher energy state should be more than that in the lower energy state in order that stimulated emission exceeds the absorption, and this is achieved by pumping, and pumping is of different types. Two of them are optical pumping and electrical pumping. In optical pumping, the electrons absorb energy from the photons that are incident and move to a higher energy state. In electrical pumping, electrical energy is used to excite electrons to the higher energy state. Laser diode is widely used in optical communication systems. It is preferred over LED in systems where a bandwidth of greater than 200 MHz is required, and the response time is very less, and therefore it supports high data rates. The spectral width is less than 2 nanometer, and therefore the intramodal dispersion is lesser and higher data rates are supported by laser, and the output from a laser is high and the beamwidth is also narrow. Therefore, the output of a laser, the power from a laser can be easily coupled into a fiber with small core diameter. There are various types of laser diodes. Almost all the laser diodes are multi-layered heterojunction devices. In fact, the double heterojunction LED evolved from the successful demonstration of optical and carrier confinement in lasers. Let us look into Fabry Perot laser. The Fabry Perot laser has two semi-reflecting mirrors placed on either sides of the cavity to form an optical resonant cavity within which light gets reflected to and fro and lasing action takes place. The FP lasers are of low cost. The double heterostructure laser, which has a low bandgap material sandwiched between two high bandgap materials to form heterojunctions, which results in carrier confinement to the active layer. And the separate confinement heterostructure laser, it has two additional layers over the heterojunction of the double heterostructure laser in order to confine the optical signal to the active region. So, the two layers which have lower refractive index are added to the double heterojunction layers, and this results in high efficiency of the laser. The distributed Bragg grating laser, this has Bragg gratings as reflectors in a Fabry Perot laser. So, gratings are nothing but periodic variation in refractive index. So, these gratings, one of the grating is a broadband grating and the other grating is a wavelength selective grating, which helps in wavelength selective feedback to the laser. The distributed Bragg grating laser provides high power and improved reliability. Distributed feedback laser, the grating is placed just above the active layer along the length of the laser, and the grating provides the feedback for lasing, and the distributed feedback laser provides wavelength stability. In quantum well lasers, the thickness of the active layer is reduced greatly to a few nanometers, and this reduction in thickness changes the electrical and optical properties of the laser greatly. And here discrete energy levels are available, and this results in higher efficiency, low current threshold and high intensity, and we have both single quantum well lasers and multiple quantum well lasers. And the vertical cavity surface emitting lasers, here the direction of emission is perpendicular to the surface of the LED, and multiple lasers can be fabricated along the surface of the LED, and this is widely used for WDM applications. So, we will look into the detail of each of the diodes. The Fabry Perot laser has two partially reflecting mirrors directed towards each other. They provide strong optical feedback along the longitudinal direction. So, the light reflects back and forth in the cavity, and wavelengths that are integral multiples of the cavity length, they interfere constructively. So, as can be seen in the diagram on the right, between the two mirrors the light gets reflected to and fro, and those frequencies which are integral multiples of the cavity length, they interfere constructively and a gain occurs and they result in resonant frequencies. The other frequencies, they interfere destructively and lose out gradually. So, these resonant frequencies, there are multiple such wavelengths which satisfy the condition. So, these resonant wavelengths, they form the longitudinal modes of the cavity. The rest of the frequencies, they gradually die out because of destructive interference. So, this is the longitudinal direction, the lateral direction and the transverse direction of a laser. In a distributed feedback laser, the gratings are distributed over the entire length of the laser just above the PN junction. So, here the cleaved surface as in a Fabry Perot laser is not required. The light emission is from the front end. So, at the rear facet there is a dielectric reflector which helps to reduce the optical loss in the cavity, reduces the current density threshold and also increases the external quantum efficiency. The various modes that are supported in a laser cavity are the longitudinal mode, lateral and transverse mode. So, the longitudinal mode along the length of the cavity, the lateral mode along the width and the transverse mode. So, the longitudinal mode is related to length L of the cavity, and this determines the principal structure of the frequency spectrum of the emitted radiation. As we have seen in the previous slide, there are many wavelengths that are integral multiples of the length of the cavity, and therefore many longitudinal modes can exist in a laser cavity. The lateral mode, it lies in the plane of the PN junction and it depends on the sidewall penetration and width of the cavity. This determines the lateral shape of the beam. And the transversal mode, it lies in a plane perpendicular to the PN junction. And this determines the radiation pattern and the current density threshold. As you can see in the picture, the transverse mode, the light after reflection forms a closed path. And this diagram gives the electric field pattern and the field intensity of the transverse modes. Now let us look into the lacing condition and resonant frequency. Only when the gain is sufficient, light gets emitted with high intensity. So the optical field intensity can be given by this expression where we consider the z direction to be the longitudinal direction. So lacing is the condition in which light amplification becomes possible in the laser diode. So for lacing to occur, population inversion must be there. That is, there must be more number of electrons in the excited state. The stimulated emission rate of a mode, it is proportional to the intensity of radiation in that mode. The radiation of intensity of a photon after it has travelled a distance z can be given by this equation. I of z is equal to I of 0 into e power gamma g h mu minus alpha h nu into z, where z is the direction that is travels by the photon and gamma gives the optical field confinement factor and g is the gain coefficient in the Fabry Perot cavity and alpha is the effective absorption along the path in the resonant cavity. So the difference between the gain and the absorption, loss due to absorption, is what determines the total intensity after the photon has travelled a distance z. Now the optical signal is reflected to and fro along the longitudinal direction in a resonator. So only those modes that have sufficient gain are amplified during each trip through the cavity. So there is a gain and loss along the cavity and only those modes that constructively interfere will get amplified after each trip through the cavity. So lacing can occur in one or many modes that have sufficiently large gain compared to the losses when it makes one round trip in the cavity. So if R1 and R2 are the reflectivities of the two mirrors, then R is governed by this equation. 2L is the distance travelled by the optical wave on one round trip. So substituting that value z is equal to 2L, we have this equation. So at lacing condition, both the magnitude and the phase of the returned wave must be equal to the original wave. Only then constructive interference occurs. So that is I of 2L is equal to I of 0 and the phase, this is the magnitude should be the same and the phase should be equal. That is e power minus j 2 beta L should be equal to 1. Only if this condition is satisfied, lacing occurs for that particular mode. So substituting the value of I of 2L is equal to I of 0 in the equation and solving, we get this expression. The gain threshold is equal to the loss along the optical path in the cavity and the loss due to the mirrors in the lacing cavity. So for lacing to occur, the gain should be greater than a threshold value. So for gain to be greater than the threshold value, pumping source must overcome the losses in the cavity. At low current values, when the pumping current is low, then spontaneous emission occurs, and here, as can be seen in the graph, this is the region where spontaneous emission occurs, and here the spectral width is large and beam width is also large. But as the current increases and it increases beyond the threshold value, then the spectral width becomes narrow and beam width also becomes narrow, and the final spectral width of a laser is approximately 1 nanometer with a beam width of 5 to 10 degrees. At very high output power levels, the slope of the curve decreases due to junction heating. So the threshold optical gain is given by beta into J threshold, that is the current density threshold, and beta is a constant and depends on the specific device. As we can see in this graph, which gives the current versus power, the optical power intensity is very less below the threshold, current threshold value. This is because only spontaneous emission occurs, and beyond the threshold value stimulated emission occurs, and therefore we have a large increase in the intensity of output light. Now coming on to the resonant frequencies, frequencies at which the resonance occurs in the cavity. So we have seen for lacing to occur both magnitude and phase should match. Now considering the case for phase condition, the phase of the original and return wave must be equal, that is e power minus j2 beta L should be equal to 1. So solving that we get 2 beta L is equal to 2 pi m, and substituting we get m is equal to L by lambda of 2n, that is the cavity resonates when integer number or m number of half wavelengths span the region between the two mirrors. So here we know the gain is a function of frequency, and there are a number of frequencies which satisfy the above equation, and each of these frequencies correspond to a mode of a laser. So we can have a number of modes that are emitted from a laser. So depending on the laser structure, we can have either a single mode or multi-mode lasers. Assuming that the gain and frequency relationship is Gaussian governed by this expression. Now to determine the frequency spacing between the adjacent modes, so considering only longitudinal modes, so the length of the cavity determines the number of longitudinal modes. So we have this expression that we have already seen. Consider two successive modes, consider two modes that are successive to each other, and let us consider their frequencies to be nu m minus 1 and nu m, and substituting in this expression m minus 1 and m and subtracting the two equations, we get the frequency spacing delta nu is equal to c by 2 ln, and we know that delta nu by nu is equal to delta lambda by lambda, that gives the wavelength spacing. So this is the wavelength spacing between two adjacent frequencies or two adjacent modes. Considering the rate equations, one regarding the photon density and another with respect to the carrier density. So the equation 1, which gives rate of change of photon density, the photons that are there in a laser, it is because of spontaneous emission, stimulated emission, and the loss is because of the photon loss. So rate of change of photon density is equal to the stimulated emission plus spontaneous emission and the photons that are lost, so minus the photon loss. And the rate of change of carrier density, we have carriers due to injection of carriers by the forward bias, and the loss in carriers is because of spontaneous and stimulated emission. So the rate of change of carrier density is equal to the injected carrier density minus the spontaneous recombination and stimulated recombination. So at steady state condition, assuming that spontaneous emission rate is 0 and the rate of change of photon density should be positive when the number of photons is less. So in equation 1 we get Cn minus 1 by tau is greater than or equal to 0. So for this value to be greater than or equal to 0, n should be greater than a certain threshold value, only then this would be a positive number. So that is, the number of electrons should be greater than a threshold value. That is what we have already seen. The number of electrons in the higher or excited state should be greater than the certain value, only then stimulated emission will take place. So population inversion should be maintained. So in order to maintain population inversion under steady state conditions, from equation 2, substituting the value of phi is 0, we get the expression n threshold by tau spontaneous is equal to j threshold by qd. So this is the threshold value of current density that is required to maintain a population inversion in the laser. Now at steady state condition at the lacing threshold, so the rate of change of photons and the rate of change of electrons is 0. So substituting in the first two equations the value and solving the expressions, we get the number of photons per unit volume phi s is equal to the number of photons due to stimulated emission plus the number of photons due to spontaneous emission. Number of photons due to stimulated emission, it is concentrated to a few modes, whereas the photons emitted due to spontaneous emission, they are spread all over the modes. The external quantum efficiency. So, that is the number of photons emitted per radiative electron hole pair that recombine above the threshold value. So, the number of photons that are emitted to the number of electron holes that recombine gives the external quantum efficiency, and it is given by this expression. External efficiency is internal quantum efficiency into the gain coefficient minus the absorption loss in the material along the path of the cavity, and this external quantum efficiency, obtaining it experimentally from the graph. So, here the external efficiency can be related to the optical power output to the current in the laser diode. So, external efficiency is Q by Eg into dP by di. For standard laser, the external efficiency is around 15 to 20%, and for high quality laser it is around 30 to 40%. Next, looking into the laser diode structures and their radiation pattern. So, we have seen the double heterojunction structure with the optical confinement. So, this confines the charge carriers and optical signals or the photons in the lateral confinement. Now, let us look into laser diode structures and radiation pattern. We have already seen using a double heterojunction layers, carrier confinement is done, and using materials of different refractive indices, optical confinement has also been carried out in the transverse direction. So, this provides optical and carrier confinement in the transverse direction. But in addition to that, lateral confinement of the optical wave and current confinement to the active layer is required to improve the efficiency and performance of a laser diode. So, let us look into some of the methods wherein optical confinement can be done and current confinement can be done. So, the various methods to confine optical wave to the lateral direction are gain guided laser, index guided laser, which has both positive and negative index waveguides. And for current confinement, there are 4 methods that are possible, and a combination of these methods can also be used. So, the preferential dopant method, the proton implantation, inner stripe confinement, and regrowth of back biased PN junctions. Let us look into these in detail. So, for optical confinement in the lateral direction, the gain guided method. So, as you can see in the diagram, a narrow metallic stripe runs along the length of the laser, and electrons and holes are injected to alter the refractive index of the layer just below the stripe. So, this way the difference in refractive index is brought and optical confinement is enabled. But these type of lasers, they have strong instabilities and highly astigmatic. As you can see, the power has 2 peak beams. Next is the index guided laser. Here this is a more stable structure compared to the gain guided structure. The waveguide structure is fabricated into the material by actually varying the refractive index in the lateral direction. So, here using index guided laser, single mode lasers can also be formed or fabricated, which would support only the fundamental transverse and longitudinal modes. So, there are 2 types of index guided lasers. One is the positive index waveguide and other is a negative index waveguide. As mentioned, in a positive index waveguide, the central region has a higher refractive index compared to the outer regions. Therefore, light is reflected at the dielectric boundary and it propagates along the higher refractive index region. And this is a very popularly used structure, and this is used for single mode lasers. And in the negative index waveguide, the central region has a lower refractive index compared to the outer regions, and at the boundaries light gets reflected and refracted. The light that gets refracted it appears as side lobes. So, as you can see, for a positive index guided fiber, the beamwidth is given as shown, whereas in a negative index waveguide, there are side lobes that appear due to refraction, and positive index waveguide is a waveguide structure that is popularly used. And in order to fabricate the index guided laser, and specifically the positive index guided laser, there are 4 different methods that we shall be discussing. So, these are methods for fabricating the index guided lasers: the buried heterostructure, selectively diffused method, varying thickness and bent layer. In the buried heterostructure method, a MESA structure is embedded in the n-type material with low refractive index and appropriate bandwidth, which enables optical confinement. So, for the 800 to 900 nanometer range, which is the lower wavelength range where gallium aluminum arsenide is used along with gallium arsenide as the active layer, whereas in the higher wavelength range where indium gallium arsenide phosphate is active layer, that is placed between the indium phosphate layers. So, this provides for a difference in refractive indices and better optical confinement. The next structure is the selectively diffuse method. Here, a chemical dopant such as zinc or cadmium is diffused into the active layer below the metallic contact. So, this alters the refractive index of the active region. And in the varying thickness method, the actual channel is etched into the substrate and layers of crystal are grown. This provides for variation in refractive index. The active layer thickness varies over here. And in bent layer, again a bent structure is obtained in the active layer, and this provides for optical confinement. Next, let us look into methods for current confinement. So, here the current flow should be restricted to the active region. So, this is achieved by having highly resistive regions on either sides of the active region or by reverse bias PN junction. So, this will prevent the current from flowing out from on either sides of the active region. And so, let us see what are the different current confinement methods available. Let us discuss in detail about each of them. So, in the preferential dopant method, a zinc or cadmium is diffused into the n-type layer, and this provides a narrow path for the current, and the reverse bias on either sides will prevent the flow of current outside the active region. In the inner stripe confinement method, a channel is etched and then lacing structure is grown above it. So, this will enable confinement of current to the active layer. And in proton implantation method, proton is implanted on either sides and it creates region of high resistivity. Therefore, the current flow is again confined to the active layer. And regrowth of back biased PN junctions, the back biased PN junction on either side of the channel, it prevents the current flow outside the channel. So, these are the different methods which enable current confinement. So, we have seen how optical confinement in the lateral direction and current confinement to the active layer. These are made in addition to the double heterojunction structure where optical and carrier confinement to the active region is already available. So, this enables improvement in efficiency of the laser. So, double heterojunction laser, the highest transverse mode that can be excited depends on the thickness of the layer and the refractive index differences. When designing a laser cavity, optical cavity, the width and thickness should be carefully chosen because a trade-off exists between the current density and output beam width. If we try to reduce the current density, the output beam width becomes broader. So, the width and thickness of the cavity design is critical. Next, let us look into quantum well lasers. So, in a double heterojunction laser, the thickness of the active layer is reduced and made very thin, and it enables confining the electrons or the charge carriers and the optical field. but the electrical and optical properties remain the same as that of the bulk material, and this limits the current threshold density, modulation speed and the line width that can be achieved. Therefore, by reducing the active layer thickness even further to around 10 nanometers approximately, then these limitations are overcome. When the dimension of the active layer is reduced greatly, there is a drastic change in the electrical and optical properties of the material. The charge carrier's movement is restricted to 2 dimensions from 3 dimensions, and the carriers can move in a direction normal to the active layer, and thereby we have discrete energy levels. So, the quantum well lasers, single quantum well lasers and multiple quantum well lasers are available. So, the quantum well is available and the flow of movement of the charge carriers is restricted to the perpendicular direction, and this results in higher efficiency of the laser and lower current threshold density. And also we have already seen the wavelength of light that is emitted by a laser or an optical source depends on the material that is being chosen. So, the band gap energy difference that determines the wavelength of emission of photon, but rather than just the material that is chosen, the thickness of the active region in a quantum well laser can also alter the wavelength of emission. So, in a quantum well laser, much shorter wavelengths compared to the conventional lasers can be achieved. Single mode lasers. So, for high speed long distance communication, single mode lasers are preferred because here intermodal dispersion is less. So, dispersion is less and it can support large data rates over long distances. So, in a single mode laser, only the fundamental longitudinal and fundamental transverse mode should exist and the spectral width should be narrow. So, the optical source, the laser should provide only the fundamental modes with narrow spectral width. We have seen the longitudinal modes of a laser depend on the length of the cavity. So, to restrict the mode to only one longitudinal mode, the cavity length can be greatly reduced. But then when the length is reduced, the device becomes difficult to handle and the output power is also less. So, other alternative solutions are seen. One of them is the vertical cavity surface emitting laser. In a vertical cavity surface emitting laser, light is emitted in a direction perpendicular to the semiconductor surface, and it has inbuilt selective grating, and since the emission is in a perpendicular direction, multiple lasers can be integrated into a single chip and it is greatly used for WDM applications. So, the active emission region volume is less, therefore, the threshold current density is less. Here 2 mirrors are indicated and they should have maximum reflectivity for efficient operation. So, for a vertical cavity surface emitting laser, the frequency selectivity can be made using Bragg reflectors. There are different types: the distributed feedback laser, the distributed Bragg reflected laser and distributed reflected laser. So, Bragg gratings are nothing but periodic variation in refractive indices in a material, and the frequency that is selected or the wavelength that is selected depends on the periods of the corrugation. So, these are adjusted to have a suitable frequency selection. So, this grating is placed adjacent to the active region and the wavelengths close to the Bragg wavelength have the maximum coupling efficiency, and the Bragg grating depends on the period of corrugations and the order of grating and the effective refractive index. So, the first method of providing a feedback is the distributed feedback grating, where the grating is placed along the entire length of the cavity just above the PN junction active layer. And here, as you can see in this graph, the longitudinal modes are spaced equally around the central Bragg wavelength, and the intensity or amplitude of the higher order modes is greatly reduced. Theoretically speaking, the zero order modes have same gain and they should be symmetrical around the Bragg wavelength, but in practice there is asymmetry in the reflective surfaces and also the asymmetry is further enhanced by difference in polishing, and therefore this results in a single mode. In the distributed Bragg reflector laser, Bragg gratings are placed on the either ends of the active layer, and they replace the mirrors in the Fabry Perot resonator and provide the wavelength selective feedback. And in the distributed reflector laser, the Bragg grating, it is placed over the active region and the passive region, and this has high efficiency and high output capability. Looking into modulation of lasers. Modulation is nothing but putting information into the light wave. Modulation can be of two types, direct and external modulation. In case of the low data rates, direct modulation can be used, and when the data rates are high, greater than 2.5 Gbps, external modulation is used. So, in direct modulation it is used up to 2.5 Gbps. Here the information directly varies the current that is driven, and therefore this results in a variation in an output optical power. But the disadvantage of this type of direct modulation is that the modulation rate depends on spontaneous and stimulated carrier lifetime and the photon lifetime. The spontaneous carrier lifetime, it is a function of the semiconductor band gap structure and also the carrier concentration, whereas the stimulated carrier lifetime, it depends on the optical density of the cavity. And the photon lifetime, that is the period for which the photon exists before it is lost by absorption or emission, this sets the upper limit to the direct modulation capability. So, the photon lifetime is much lesser compared to the carrier lifetime. Therefore, laser diodes can be used for pulse modulation. And so, in pulse modulation, the modulation rate is basically limited by the spontaneous carrier lifetime, which is greater than that of the stimulated carrier lifetime. So, in the case of pulse modulation, when a current pulse is given, the output optical intensity should also vary. So, the time required to achieve the population inversion on giving a current pulse is given by Td is equal to this expression, where Ib is the bias current and Ip is the amplitude of the current pulse. So, this delay time Td can be eliminated by providing suitable DC biasing to the diode at lacing threshold. So, in this case the delay time becomes 0 and the output optical pulse can change as soon as the input current pulse changes. So, when with DC biasing of the diode, the carrier lifetime is only due to stimulated emission lifetime, and therefore high modulation rates are possible. And for analog modulation, the drive current should be greater than the threshold current, and it should be proportional to the baseband information of the signal. And a linear relationship between light output and current input is required, and due to non-linearities, various intermodulation and cross modulation occurs, and which distorts the signal, and therefore distortion compensation techniques are required. So, in case of high data rates, external modulation is carried out. Here the steady output from the laser is modulated externally by an external device. There are two types of external devices available. One is the electro-optic modulator and the other is the electro-absorption modulator. In the electro-optical modulator as shown in the figure, it is made of lithium niobate, and the light beam is split into two parts, and in one of the parts the electrical signal changes the phase of the signal, and the two signals are combined again, and these combine constructively or destructively to produce a 1 or a 0 pulse depending on the electrical pulse that has created a phase shift. In the electro-absorption modulator, which is made of indium phosphide, the electrical signal changes the property of the material itself over which the light path travels, and thus it makes it transparent to a 1 or 0 and helps in modulation. Coming on to the temperature effects of a laser, the laser is highly temperature dependent, and the threshold current depends on the temperature given by the expression I threshold is Iz into e power T by T naught. And so, as the temperature increases, as you can see in the graph, the threshold current increases, and the lacing threshold also increases with aging. Therefore, in order to maintain the threshold current value, DC bias current level has to be adjusted in a laser. So, the different methods to adjust and maintain a constant output of a laser in spite of the variation in temperature and in spite of aging are optical feedback scheme and thermoelectric cooler. These are two of the methods. So, optical feedback scheme, a feedback is taken using a photo detector of the output optical power, which is compared with the reference value, and then the DC bias current value is varied to get a constant output power. In the thermoelectric cooler method, the constant temperature of the laser is maintained, which stabilizes the output level. So, in this video we have seen the basic principle of operation of a laser and a number of laser configurations and various types of lasers, and how to confine optical and carriers in a laser, and also the current confinement and optical confinement in the lateral direction. And then we have seen the derivations for the lacing condition, the resonant frequencies and the efficiency of a laser. We have also seen the single mode lasers and also the modulation and temperature effects of a laser. These are the references. Thank you.